Okay, so let's get a start on the questions. So we'll spend more time on induction than motor, but we'll just quickly run through them as well. So here, you've got a positively charged ion traveling 250 meters per second between two parallel charged plates, M and N. There's a magnetic field present as well between the two plates, and the direction of the magnetic field is shown. Ion is traveling perpendicular to both. And they give you numbers for that as well. And the key point is it passes through undeflected. So what's the magnitude of the adjusted magnetic field and the polarity of the M relative to N? All right, so use your right-hand push rule. Positive charge going to the right, magnetic field going into the page. That means, of course, that the magnetic field is pushing the charge up. Since it's passing through undeflected, we can assume that the electric field is pushing the charge down. If the electric field is pushing the charge down and it's a positive charge, that will suggest that that is positive and that is negative. So we already know the polarity of M relative to N is positive, restricting our answers to A and B. Oh wait, sorry, A and C. So now we just need to actually do the calculation. Well, remember QVB is FB and QE is your force from electric field from year 11. Q just cancels. We know V, we know B. We want to find B. So B here is going to be E over B. E is given as 200. B is given as, V is given as 250, which is 0.8. So that means the answer will be A. All right, so there's a lot of motor questions here. All right, let's just do one which is not 90 degrees. So a current 5 amps flows in a wire that's placed in a magnetic field of 0.5 Tesla. Wire is 7 meters long and an angle of 6 degrees to the field. So basically, it's a pretty straightforward question. We've got a wire carrying current. It's 5 amps. We've got a length. We've got an angle. We've got a magnetic field strength. This is direct application of F equals VIL sine theta. Of course, in an exam, you should be writing out all the things given. So you should be writing the formula like I've done there. Write B equals 0.5 Tesla. Write I equals 5.0 amps. L is 0.70 meters. And theta is 60 degrees. And so you just sub all that in. Okay, so here you'll get an answer of 1.5, 1.52 or so newtons. Now, it simply says calculate the force on the wire. So we won't do much more than that. But we should probably
also
that.
oh, right.
Yeah, but we should probably also note, of course, that when you have your question, you should also pay attention to significant figures. So you've got 5.0 amps. You've got 2 significant figures here, 2 significant figures here. And so all the numbers that they're giving you are in 2 significant figures. So in the exam, you're often going to have marked down for significant figures at some point. All right. It won't be in every question, but it will be one question. And so that question is normally pretty easy to see in the exam because they'll give you something in all the same number of significant figures. And here, all of them are 2 significant figures. So you should, of course, then adjust for that and say that's 1.5 newtons to 2 significant figures. All right. Now they've asked you to calculate the force on the wire and not ask for the direction, but we should probably just quickly also take a look as well. So we understand that the current is flowing down and to the right. So because the current is flowing down, okay, then you can basically, this part is no force experienced. So if you have the current going down and the magnetic field going to the right, then your right-hand palm rule tells you that the direction, not that you need it for this question, is out of the page. And indeed, this is a fairly simple question, but I just wanted to demonstrate one when it wasn't 90 degrees, because we have done that quite, we've so far only talked about 90 degrees. Okay, so question 13. We've mentioned before, when a charged particle is in a magnetic field, it goes in a circular path, as we've got here. If the speed of an electron is increased, what correctly shows the effect of this change? So you understand, of course, that force of the electron is Fb, which is QVB sine theta. Here, theta is 90 because, of course, it's 90 degrees to the plane. So it's QVB. So clearly, V goes up, force on electron increases. Right? And then the radius of the path, well, we can derive it, but basically, the issue here is the centrifugal force required is mv squared over r. Now, if you're increasing the velocity, then the central force required is greater. Now, force does go up, but not by enough, right? Because the force you need goes up by the square, whereas the force that you get just goes up by power 1. In other words, you're not going to get enough force to meet the centrifugal force, which means it's going to start spiraling out, which means it's going to be increase and increase. Now, of course, if you're familiar, or you want to derive it and you let F, FB equals FC kind of thing, you'll note that the radius will equal mv over qb. So if you let the radius be mv over qb, noting that m, b, and q are constant, and as v goes up, the radius will go up. Both of them, whether you think about only in terms of FC in relation to qb, conceptually, or derive the formula, the answer is increase, increase. Let's try to get onto induction. So we've done questions like those. These are all on electric fields and magnetic fields, which hopefully, based on our prior work, you hopefully are familiar with. Okay, so just quickly saying here, you've got charged particles with different radii. All right. Now, they ask why they're in different directions. Clearly, it's because one's positive, one's negative. Okay. Circular, we've explained that. Okay, basically because it's charged particles in magnetic fields, which means the magnetic force is always going to be perpendicular to the velocity, which then relates to your centrifugal acceleration. Now, we've already derived the formula for that, but just using this as an example, just note that typically most questions you're going to get are relating to electrons and protons. Now, because the radius equals mv over qb, as we've sort of talked about before, assuming they're in the same magnetic field, then and going at the same velocity, then it's really the charge to mass ratio that matters, right? So if you assume v and b are constant, so for particles moving at the same velocity and in the same magnetic field, then it really depends on how heavy they are in terms of mass and how charged they are. Now, in the case of a proton and an electron, well, they're both positive or negative 1, so that the charge is the same. So the thing is then, it's a question of the mass. And you should know that the mass of a proton is much, much, much more than the mass of an electron. So typically, under most circumstances, you end up with this having a larger radius and this being a much smaller radius, significantly smaller radius. So that typically is what you see in most of your questions. So you might want to keep that in mind. Of course, it's not guaranteed though, so you just need to sort of pay attention on a question by question basis. Personally, for electrons and protons traveling at the same velocity in the same magnetic field, you assume that, well, you would get a smaller radius for the electron. All right, so now we're getting into questions about forces between two wires. And I note that there was a question you wanted to go through in Deacon, so I'm going to try and find it. But the key thing to remember, of course, as we discussed earlier, is you've got two wires in the same direction, both carrying current, then they will experience a force, all right? If they're going in the same direction, then they will attract. If they're going in opposite directions, they will repel. Just remind me, Deacon, it wasn't this question, was it? It was very similar, but it wasn't this one, right?
Yeah, I think you can just do that one, I'm guessing.
That's fine. I can find, I mean, you know, it's very similar, but I'm sure I can find this one. Yes. I believe it was this one. Right. So here, the balance was used to investigate the relationship between current and force. The balance was set up with one copper fixed to it and a second rod fixed above it, as shown in the diagram. Each rod was connected to a source of current, and the diagram is not shown to scale. Okay. The copper rods were rigid, each 2.6 meters long and parallel. Current in the upper rod was kept constant as 50 amps. Different currents were passed through the lower rod. Okay, so you have 50 amps going through this one, and that's not changing. Different currents will pass through the lower rod. Some I, this varies. And you read the balance, and they're given in the below. So let's take a look. As you increase the current, what happens to your readings? Well, you go 0.5485, 5480, 5474, and so on and so on. So as you go down, the current increases, but the balance reading decreases. So that would suggest that as you increase the current, the force you're getting is upward. So this tells us that the force on the wire due to the current is upward. Hence the balance readings going down. Which then, of course, suggests to us that if the force is upward, then that means it's an attractive force between the wires. And if it's an attraction force between the wires, then that means they are in the same direction. So I don't know if they're both going left or if they're both going right, but they are definitely both going in the same direction. Okay, so we definitely need to sort of examine that before we look at the question further. And then we probably need to do something in terms of readings. Maybe we'll look at the questions before we do that. A. And if okay, so we just did that, right? We worked out that the directions in both rods are the same, and we've given the reason why. And so the next thing I want us to plot, okay, that might be, I'm going to have to reproduce the table. Give me a moment. All right, so that's our data there on the left, which we'll need. And let me just clear the other things on the screen. All right. So now we will need to plot the data. Now, often you're given an exam to plot. In this case, they've drawn out the curve. They've labeled the axis for you with units, and they've also plotted out the axis for you as well. Just remember, if you are, if that's not done for you, you need to definitely label your axes. Definitely put units in your axes. And also, when you're picking a scale for your horizontal and vertical, you want to pick a scale that uses most of the graph. So don't stop the graph here or don't stop the graph here. You want to use up most of the graph paper, like sort of 80–90% of it, roughly, right? Certainly more than like 60%. Okay. So we need to plot it. So let's magnify that a little. And with plotting, remember as well that you're going to use crosses or dots with circles around them. So in this case, we've got a current of 2.8. So it's going to be here, and it's 0.5485, which is going to be here. And then you've got 8.0, which is 0.548. Then you've got 12.2, which is 0.5474. Then you've got 16.8, which is 0.57. Then you've got 20, which is 0.5465. Okay, so there is your plotted points. After that, of course, you need to draw a line of best fit. And I'm probably just going to eyeball it roughly. Something like that appears reasonable. There's always going to be some error, especially with a sort of, one done visually. You would typically do this with computers, but the HSC will allow for sort of some variation. Just make sure that you understand you don't have to go through the first point or the last point or any of them. Okay, that's typically a common misconception. And yeah, you do need to just recognize you're just trying to get the line of best fit, which may not go through any of your points as well. So yes, you can most definitely sometimes need to draw the graph from scratch, which I think I covered. Let me know if there's still any outstanding questions on that. All right, so we now have the graph, plot the data using the scales and axes. And oh, yeah, so they've been very clear about what you need to do here, which is very nice of them. But just make sure, even if they don't tell you that, you actually still need to do that. Okay. Find the mass of the copper rod on the balance. All right, so this is now where we need to oh, I should have drawn the line of best fit a bit further. All right, let me extend the line of best fit. Let me extrapolate. Okay, let me draw it again. Something like this. And you may see why I wanted to extrapolate, because if I extrapolate it, for 1 mark, it's very easy. To find the mass of the copper rod on the balance, we just use our line of best fit and go, hey, if we didn't put any current through, then of course, there's not going to be any force of attraction on the rod. If there's no force of attraction, then your balance should give me the reading. And so we're going to estimate the mass of the copper at 0.5489 kilograms. Now we need to calculate the distance between the 2 copper rods. Okay, so given that we understand the mass is 0.5489, we now need to take advantage of our force. All right, so it's better to use this. Now this is the balance reading, which is kilograms, which is M. Now you understand that basically that the force that the balance reading measures is going to be weight minus the force of the it's the weight minus the force of the attraction. Okay. Now, when we're going to also use the graph, of course. All right. And typically, when we draw a line of best fit, we might want to consider what the gradient is doing. Okay. So with the balance reading, it's an mg. It's the m, right? Because it's a balance. Well, I mean, it's the force, but measured in units of mass. So to actually get the balance reading, which is, I suppose, a force, but in terms of newtons, you need to then get all of these numbers and multiply it by 9.8, right? So to get the net force experienced, you need to get the mass of the reading multiplied by 9.8. And this net force is then also going to be inclusive of your weight force minus the attractive force. Now, the weight force we're going to assume is constant at, or basically 0.5489 times 9.8. So this gradient, okay, you think of it as the gradient is going to be the change in the balance reading, in kilogram, divided by the change in current, which you can convert by multiplying by 9.8. So it's the change in force over I. Now, recognizing that F over L equals K I1 I2 over D, then F over I1 equals K I2 times L over D. Now, this F over I we can get from our gradient once we adjust for the 9.8 in the numerator. K is known, I2 is known as 50, given in the question. L is known, given as 2.6 in the question. So 2.0 times 10 to the negative 7 times 50 times 2.6 over D. And as long as we can work out the gradient, okay, so the gradient as using the units on the axis is currently kilograms over I, all right? So basically, what you need to get F over I is you need to get the gradient of our curve, of our line of best fit, multiplied by 9.8. That's what we're going to get. The gradient is kilograms over I times 9.8 will be newtons force over I, which is what we want. And then we can solve for D. So in other words, the D that we want to get is going to equal 2.0 times 10 to the negative 7 times 50 times 2.6 all over the gradient of our curve times 9.8. We just now need to work out the gradient of our curve and sub all those numbers in. Remember, when we're working out gradient, it's of the line, not the start and ending points. So we'll just try and pick nice points that we can read off. So like here. So that's a point of, we read off a point of 16 and 0.5470. You can read off a point here of 0.5489. That gives me a gradient of 0.5470 minus 0.5489 all over 16 minus 0 gives me, well, a small number, something around negative 1.19 times 10 to the negative 4. I'm going to sub that number in, and we're going to get an answer for D. Giving us an answer of 2.23 times, so basically 2.23 centimeters is your answer. Now, you would have got a negative answer because of the negative gradient, but remember that we were really more concerned about the magnitude of the gradient as opposed to whether it was positive or negative. So hopefully that addresses that question, okay, and also shows you how we can use some of some experimental questions. Let's get on to induction questions now. So taking a look at this question, for example, you've got a drill which is spinning. Okay. It's got a magnet attached to it. So basically you've got a rotating magnet. Okay. And you're told that the drill starts from rest and gradually speeds up, reaching full speed after 3 revolutions. So the key point here is that the drill rotates 3 times, and that each time is faster. So you want to sketch a graph showing the induced EMF across the coils during the time that it takes the magnet to reach full speed. All right, so I'm going to sort of eyeball this, but basically you understand that because this is time on the horizontal axis, hopefully it makes sense that every time you spin, right? Hopefully it makes sense that every time you spin, you're going to get sort of an induced current, once when the North Pole's going towards you, once when the North Pole's going away from you. So that's one sort of revolution. Now, you could probably do it a little bit better than that, but for now, let's just do that. So if that's the first spin, recognizing that it spins faster, then the second spin should be less than that. So maybe I've gone too far. Okay, so let's say the first spin is that far. The second spin, let's say it's this far. So you can see it's noticeably shorter by a little bit. And the third spin, let's say it's this far. All right, so that's the first spin, that's the second spin, that's the third spin. Now, because it's speeding up the whole time as well, if we consider the halfway mark to be here, and we consider the halfway mark to be here and here, then really it should sort of cross after that. So I'm going to cross somewhere here, somewhere here. That looks too much over the halfway mark actually. And it's going to sort of, I'm going to actually cross after, because basically the first half should take longer than the second half, right? So it's not a symmetrical sine curve, right? And now the next thing you need to consider, apart from just, when it crosses the lines, is how high it goes. Now we're graphing induced EMF. And you might recall from our earlier revision that induced EMF is related to the rate of change of flux. So in terms of the rate of change of flux, because you recognize that for every turn, you're introducing the same change in flux to the coil because it's the same magnet and you're still doing one turn. So your numerator is essentially not changing. This numerator is essentially constant. For every turn, that numerator is constant. But we recognize that your delta T is changing, right? Because you're spinning faster. So this is decreasing. So if you've got a numerator that's the same, but a denominator that is getting smaller, then that means this is increasing. So when we draw our curve, you're going to basically get something that kind of looks like a sine curve, but it's a sine curve that's getting bigger. So if you want to sort of model it, you can think of it like a sine times an exponential kind of thing to show it's sort of not damping, but like that, right? Those will really be the key things they're looking for here, right? The fact that the time is getting shorter for later turns. Of course, you've got your positive, negative, positive, negative, positive, negative, induced EMF, opposing signs, and there's 3 sine curves, but asymmetrical, getting more cramped in terms of the period, the frequency is getting higher, and your amplitude is getting bigger. It's basically it. Not constant amplitude, not constant period. Let's try and get a few more questions out of the way. So we mentioned high voltage transmission lines that contribute to safe transmission of electricity. I don't think that's really tested anymore. That's questions really asking about safety, but you basically will just need to mention about how it's the design of the safety, which I don't think is really tested anymore under the new syllabus. You'd be talking about how they insulate the wires. Well, not so much the wires, sorry, but how they separate the wires from, I guess, things that are close, and the fact that they insulate it from the tower using these particular things that increase the distance and prevent dust getting on them, and so forth. Fuses and safety is also not really tested in year 12. If anything, that's more of a year 11 thing. And under the old syllabus, year 11 is not really in the new syllabus in year 11 or 12, but it is all circuit breakers for that matter. But it's more crucial science, and you should know that from earlier work, but unlikely to be tested in HSC, both under the new and old syllabus for fuses and circuit breakers and things. That was more a year 11 thing. Okay, under the old syllabus. Okay, so here you've got a question showing a model of system used to distribute energy from a power station through transmission lines and transformers to houses for 6 marks. During the evening peak period, there is an increase in the number of electrical appliances being turned on in houses. Explain the effects of this increased demand on the components of the system with reference to voltage, current, and energy. So again, this might seem more a question that's more related to the older syllabus from prior to 2019, but it's not impossible that they could ask you this question, I suppose. It is still relating to transformers and so forth. So they really want you to explain the increased demand of the components of the system with reference to voltage, current, and energy. So what I mean they really want to get at here is, as demand increases in, I guess, this sort of demand circuit, okay, as demand increases, that means the power required goes up. Okay, so they're drawing more current. Okay, so if you don't supply more power, so if there is no adjustment made, by drawing more current, then the voltage will drop. The houses will experience a voltage drop at the consumer side if no adjustments are made at all. And that's basically why they do adjust it in real life. They constantly monitor and adjust. But you may have heard of blackouts, which is when you lose power, right? When there's a break in the circuit. But also what happens as well, which you may not be aware of, is what's also called a brownout. So basically, when not enough power is supplied, you get voltage, but not enough for your appliances to work properly at the right voltage. And so that's what's called a brownout. And in fact, if you might recall, during the bushfire seasons and so forth, when it was really hot, they basically shut down certain industries in the state which use a lot of power to try to make sure that they've got enough power, because your power plants are limited after all, to give to the people that are going to turn on the air conditioning. Air conditioning is very power intensive. And not only that, they also, and sometimes you have blackouts because what they do to try to manage power is, because they can't supply power to everyone, they kind of just shut down an area and say, you guys go without power for like 3 hours, then they'll give them back and then shut some other place down. So basically like kind of just, doing a sort of group 1, group 2, group 3 thing. Kind of like the way they're dealing with vaccines now, do this group first, then that group, is to try and sort of get through everyone in that sort of sense. All right, so that is then going to do that. So this component will have a voltage drop. And so to account for that, what we often would then need to do is you need to provide more power. Okay, so that would increase the current flow to meet the demand. Okay, the power station will need to increase output. Which would then, typically the transformers are fixed, right? The ratios are fixed. So it's not like you can just suddenly change the ratio on the transformers for most of them, especially for high voltage. So when the power station increases the output, typically will both the voltage and the current, but typically more so the current, more the current than the voltage will increase. That will then be stepped up in transformer 1. This transformer 1 will then step it up to a very high voltage. So the transmission wires will then transmit the power to transformer 2. The current will be a bit higher than before, okay, compared to during the day, say, which will then step down the voltage. Now, because there's more current, we would expect comparatively more power loss here, and also more power loss in all components, in fact. Right? But then the step down the voltage, which will then increase the demand to meet the demand. By having more current and similar voltage, it will then be able to provide more power to the houses. And essentially, that's essentially the effects of the increased demand on the components of the system. Okay, voltage will firstly drop with an increase in current due to the increase in energy. To meet that demand, we need more energy from the power station in terms of power. So it's technically power, which is energy over time, which then will increase more so current and less voltage, but there will be a slight effect on voltage in this circuit here, which then increases the current here. Hopefully voltage has stayed relatively constant, but it will go up slightly. It will go up slightly. And then that will then allow this to supply and meet the demand. Okay, so hopefully that addresses that question. Okay, so if we take a look at this question, you've got the diagram shows an electric circuit in a magnetic field directed into the page. And here, the graph shows how the flux of the conductive loop changes over time, over 12 seconds. So this is flux. You have to pay attention to your axes whenever you look at a graph. This is a flux in time. Okay. So you want to calculate the maximum magnetic field strength with a stationary loop during the 12-second interval. Well, remember, magnetic field strength is basically magnetic flux density. So if you want maximum B, then you want maximum phi. This graph is phi. So maximum is 0.6 for the maximum. And the area you're told is, well, you're not told. So you're going to have to work it out. There's a circle. So it's pi r squared, which is pi 0.3 squared. And then that will give you 2.12. Making sure, of course, that you're doing everything in terms of SI units. Okay. So if that's the maximum magnetic field strength, they now want us to calculate maximum voltage generated in the circuit by the change in flux. All right. Well, remember, this is just delta phi over delta t. Now you want to calculate the maximum voltage, which means we really want the maximum delta phi over delta t. Now this is phi, and this is t. So delta phi over delta t, in other words, is the gradient of the graph. And you want the maximum gradient. So if you examine this, that's the gradient. It's going up. This is 0. There's no EMF here, but this is certainly much steeper. So this is when you've got your max gradient. It's negative, but in terms of like the positive and negative can affect the direction, but in terms of how big the EMF is, we just care about that. So let's calculate that gradient. I mean, this is in terms of Weber and seconds. So the gradient will be it. So it's going to be 0.6 over, ignoring the negative sign. Okay, I don't care about the negative sign. I'll care about it for direction, but not for the magnitude. So it's 0.6 over 2, it's like 12 minus 10, right? So that's going to be 0.3 volts. Okay. So that, now let's consider direction. So if the flux is going into the page, so if we assume all of this is into the page, so if we assume that the positive flux is into the page as per their diagram, and if it was out of the page, it would be negative, then in this time period from 10 to 12, the flux is going from very into the page to, well, nothing. In other words, the change in flux is out of the page. It's going from into the page to nothing, so it's in the out of the page direction. So if the change in flux is out of the page, that means by Lenz's law, you will want to create an into the page. Okay, it's going to create an into the page. And using a right-hand grip rule to create an into the page, that means it would induce a current in the clockwise direction to create and try to counteract this change. It's going to create a magnetic flux into the page inside the coil, right? Inside the coil. I don't care about outside the coil. It's inside the coil. So it's going to generate that. So if the current is flowing this way, then that would suggest that Q is positive and P is negative, because this is conventional current. I. So Q is the positive terminal and P is the negative terminal. Okay. I mean, questions like this are pretty sort of often come up. So just make sure you can apply the induction concepts that we covered earlier to do those. Okay, so let's go through this question. So you've got a strong magnet is at rest a few centimeters above a solid metal disc made of a non-magnetic material. The magnet's then dropped, and you've got a graph showing the velocity of the magnet, which clearly has a linear section here, and then this kind of idea. So account for the shape of the graph. Well, you've got a linear section to start with a stated gradient of 9.8 negative. That might sound familiar to you. So you might want to firstly account for that. So the linear section of the graph has a gradient of 9.8 and is negative, showing a constant acceleration of 9.8 meters per second downward. And this is because the magnet is falling under the influence of gravity, which we understand, of course, is going to have a constant acceleration over reasonable values of like distance and so forth and so forth. All right, so it's falling under the acceleration due to gravity, sort of close to Earth. However, when it approaches the non-magnetic metal disk, the strong magnet, being a magnet, will cause a change in flux for the metal disk. Okay, it's going to experience a change in flux, which by Faraday's law will induce an EMF, and by Lenz's law will induce a current which opposes the drop. So by Lenz's law, an induced current, or current will be induced, I should probably say, in a way that opposes the movement of the magnet towards the disk. And that therefore will decelerate, thus decelerating the disk. This results in the upward non-linear section of the graph. Then finally, once on the disk, the magnet is at rest. And hence, graph is horizontal. So basically, you've got like three sort of phases to this movement, I suppose. The first phase is the drop, right? It falls under gravity. And then it gets closer, which then there's an interaction with the disk through induction, Lenz's law. And then that will slow it down, but it won't stop it going down. And then it will still get to the disk. And once it gets to the disk, then it will, well, just be on top of it. So, your weight force equals your normal force. Okay. Did that address the questions, Deacon, that you have?
Oh, can I unmute, right? Oh, yeah, it does.
Okay. All right, great. So in that case, you guys have the booklet, so you can, continue working through questions on these, obviously, get a bit more practice. Now, in the meantime, we'll work on Module 7 tomorrow. Try to get that out of the way tomorrow, so that gives us the next 2 days after that to work on Module 8, which I understand you guys are both keen to get to. So give the questions a go, and I'll see you all tomorrow.
Oh, okay. Bye.